In a previous video, we looked at some identities involving the Riemann-Zeta function. And in this video, what we want to do is build upon those identities to create some new identities. So let's go ahead and recall that the Riemann-Zeta function is defined as follows. Zeta of s is equal to the sum as n goes from 1 to infinity of 1 over n to the s. And I should say that technically the Riemann-Zeta function is the analytic continuation of this sum, but we won't really get into that. So the even values of the Riemann-Zeta function are particularly nice. So zeta of 2, in other words, the sum of the reciprocal of the squares is pi squared over 6. So that's a famous sum by Euler. And then zeta of 4 is pi to the 4th over 90. And so previously we proved the following generating function. So I'm going to call it f of x for this video because it'll be useful to have a name. And so it'll be the sum, k equals 1 to infinity, of the 2k value of the zeta function minus 1 x to the 2k. So it's the generating function of this sequence, which is given by zeta of 2k minus 1. And we proved that that's equal to x squared over x squared minus 1 plus 1/2 times the quantity 1 minus pi x cotangent pi x. And then I want to point out that if we look at f of 1, that's equal to the sum k equals 1 to infinity of zeta of 2k minus 1. And then we did this by taking the limit of the right-hand side, because notice we have a pole here, or a discontinuity in the right-hand side at x equals 1. But you can take a limit. You have to use L'Hopital's rule a couple of times. But what you end up with is that this is 3/4. So I'm going to go ahead and put that over here. So f of 1 equals 3/4, because that's going to be useful to have as we move on. Okay, so the game I want to play is I want to evaluate this at a different value instead of x, maybe I times x, to see what we can get out of it. So I'm going to go ahead and erase this that we had in a different video so we can get to this new problem. Okay, so now we're ready. So like I said before, we're going to replace x with I times x, and that's going to give us f of I times x is equal to the sum k equals 1 to infinity of zeta of 2k minus 1 times I times x to the 2k. So we can obviously simplify that, but we'll do that in the next step. And this is going to be I times x quantity squared, I times x quantity squared minus 1 plus 1/2 times the quantity 1 plus I times pi x times cotangent of I times pi x. So now there's a little bit of simplification that we can do. So notice that this sum is going to be equal to the following. So this is the sum k equals 1 to infinity of minus 1 to the k times zeta 2k minus 1 x to the 2k. Okay, so let's see why this is the case. So let's notice that I to the 2k is the same thing as I squared to the k, but I squared is -1, so this obviously gives us -1 to the k. Okay, so now let's go ahead and look at what happens on this right-hand side. So notice that's going to give us minus x squared over minus x squared minus 1. That's what we get for that first term. And then we're going to have plus 1/2 1 plus I pi x cotangent I pi x. And we're going to have to take care of this cotangent of I pi x term. But before we do that, I'm going to go ahead and point out that this is x squared over x squared plus 1, so we can make that simplification. Okay, so I'm going to clean up this bit of the board, replace it with where we are, and then we can start working on this cotangent of I pi x term. Okay, so in our previous step we have the following, this f of ix, so this function evaluated at ix, so that's going to be this alternating sum version of this generating function for zeta 2k minus 1, so that's going to be equal to x squared over x squared plus 1 plus 1/2 times the quantity 1 minus I pi x cotangent I pi x. So you know that something is up with this term over here because there are complex numbers in it, but in the left-hand side there are no complex numbers. So that should simplify. And let's see how that can work. So notice we have the following. So cotangent of theta equals cosine of theta over sine of theta. So that's like a well-known identity. That's how cotangent is defined in a sense. And this is equal to e to the I theta plus e to the minus I theta over 2. So that is what cosine theta is. And then sine theta is given by e to the I theta minus e to the I theta over 2I. So like I said, this numerator whole thing right here is cosine, and this big denominator is sine. And you might say, well, where does that come from? And it comes from Euler's formula. So let's recall that e to the I theta is equal to cosine of theta plus I sine of theta, and then e to the minus I theta is equal to cosine of theta minus I sine of theta. So in fact, that just gives us a system of equations that we can solve for cosine and sine. Okay, so now let's notice that we can simplify that a little bit. So notice that we have these 2's which can cancel. This I, which is in the denominator of the denominator, can come up to the numerator, and that will give us I times the quantity e to the I theta plus e to the minus I theta over e to the I theta minus e to the minus I theta. So we've got something like that. But now notice maybe the next thing that we can do is we can multiply the numerator and the denominator by e to the I theta. And that's going to cancel this e to the minus I theta. So let's see what we get if we do that. That gives us I, e to the I, well maybe let's write it like 2I theta plus 1 over e to the 2I theta minus 1. So we can use that as our formula for the cotangent of theta. So the cotangent of theta is this guy right here. Okay, so now let's clean up the board, and then we'll use that in order to simplify this cotangent of I pi x. Okay, so in the previous board we calculated this version of cotangent of theta. So cotangent theta is I e to the 2I theta plus 1 over e to the 2I theta minus 1. Now we want to use that in order to simplify this cotangent of I pi x. So in other words, we'll take this formula and we're going to set theta equal to I pi x. So let's see what that gives us. So that's going to give us, I'm just going to bring this part down, so we get x squared over x squared plus 1 plus half, and then we have 1 minus I pi x times another I. So notice I'll just put the other I in there and we'll simplify it later. And now we have this cotangent of I pi x. So that's going to give us e to the 2I times pi x. So that's going to be minus 2 pi x plus 1. Okay, so let's reiterate how that happened. So the 2 is part of this formula. This I right here and this I over here combined together to give us minus 1. And then the x is in there because that's part of what we're setting theta equal to. So that's what we get there. And then similarly in the denominator, we're going to have e to the minus 2 pi x minus 1. So we get something like that. Now let's notice we can do a little bit of simplification. So this I and this I can cancel, and that'll give us a minus 1, which is going to cancel that to a plus Good. And then maybe this thing is a little bit awkward because we have these negative exponents. So let's go ahead and multiply by e to the 2 pi x over e to the 2 pi x in order to simplify that. And I should say we're only multiplying this term by that. So that's going to give us x squared over x squared plus 1 plus half, and then 1 plus, so we have pi x still, and now this is going to be e to the 2 pi x plus 1, and so the e to the 2 pi x is from multiplying this by 1, and then we get 1 by multiplying e to the minus 2 pi x by e to the 2 pi x, and now we have 1 minus e to the 2 pi x. So we've got something like that. But now, this is still a little bit awkward because we have this 1 minus term. I'd rather have this e to the 2 pi x kind of as the leading term. So what we can do there is switch the order of these and pick up a minus sign right here. So that's going to give us x squared over x squared plus 1 plus half times the quantity 1 minus pi x times e to the 2 pi x plus 1 over e to the 2 pi x minus 1. So to reiterate, essentially what I did is I multiplied by negative 1 over negative 1. The negative 1 in the numerator came here, and the negative 1 in the denominator switched those. Okay, so now we've got a nice formula for this alternating sum. I'll bring this thing to the top and then we'll move on. Okay, on the previous board we finished up this calculation. So f evaluated at ix, on the one hand, it's this alternating sum of these values of the Riemann-Zeta function minus 1, but on the other hand, it's equal to x squared over x squared plus 1 plus 1/2 times the quantity 1 minus pi x e to the 2 pi x plus 1 over e to the 2 pi x minus 1. So now, notice we can evaluate this guy at x equals 1, and that gives us a new identity. So if we do f of I, in other words, this thing evaluated at x equals 1, that's going to give us an alternating version of this identity right here, which led us to f of 1 equals 3/4, which again was from a previous video. So in other words, that's going to give us k equals 1 to infinity of minus 1 to the k zeta of 2k minus 1. So that alternating sum is going to be equal to, so plugging in x equals 1 for this, we're going to get 1/2 for this term. So it's 1 over 1 plus 1. And then we're going to have plus 1/2 times the quantity 1 minus pi times e to the 2 pi plus 1 over e to the 2 pi minus 1. So we get something like that. But notice we can simplify that a little bit. Notice we're going to have 1/2 plus 1/2, so that's going to be 1 minus pi over 2 e to the 2 pi plus 1 over e to the 2 pi minus 1. Okay, great. So that's what we get for this alternating version of the sum that we had up here. So now what I want to do is put these two together in order to get like a nice new identity. All right, so I'll clean up the board and then we'll get to that. Okay, so let's summarize where we are so far. So in a previous video we proved this identity. So the sum k equals 1 to infinity of zeta 2k minus 1 was 3/4. I'm going to go ahead and call that S1 for sum number 1. So that's from that previous video like I said. And then sum number 2, S2, that's the alternating sum of zeta 2k minus 1. So we have this minus 1 to the k out front. And notice that's going to give us 1 minus pi over 2 e to the 2 pi plus 1 over e to the 2 pi minus 1. Now what I want to do is see what we can do with these two sums to make two new identities. So let's first notice that if we take 1/2 sum 1 plus sum 2, that's going to be equal to 1/2 times the sum k equals 1 to infinity of, well notice everything is the same. We have these like terms, but this one has a coefficient of 1 and this one has a coefficient of negative 1 to the k. So we can write this as 1 plus negative 1 to the k, and then we have zeta of 2k minus 1. So that's what we get on the left-hand side from adding these two sums up. So just to reiterate, we have these like terms, which are the zeta of 2k minus 1. This one has a coefficient of 1. This one has a coefficient of minus 1 to the k, so that's what we get. Great. Now, if we add the right-hand sides, we get 3/4 plus 1. So notice that's going to be 7/4. And then I should say we've got to multiply this whole thing by a half, because I'm multiplying the whole thing by a half right here and right here. And then we have this is minus pi over 2 e to the 2 pi plus 1 over e to the 2 pi minus 1. Okay, good. So now let's go ahead and simplify this right-hand side while we're at it, because that's simple. So notice that's going to be 7/8 minus pi over 4 e to the 2 pi plus 1 over e to the 2 pi minus 1. Okay, great. And now notice what happens to this right-hand side. So if k is odd, this is 0, and if k is even, this thing is 2. So let's go ahead and write that real quick. So notice that this is equal to 0 if k is odd. And why is that? Because we have 1 minus 1. And this is equal to 2 if k is even. Okay, good. So what that means is that this 2 out front is going to cancel this half, and what we end up with is the sum k equals 1 to infinity of k only being even numbers. So I really can just say k equals 2 to infinity over only even numbers of zeta of 2k minus 1. But finally, what I can say is that since I'm only going over even numbers right here, I can re-index. And so I'll re-index by sending k to 2k. And what that will do is re-index my sum, where I'm summing over all the numbers 1 to infinity. And then I have zeta of 4k minus 1. Like that. Okay, great. So let's look at why these are the same sums. So this is summing only over even values. So k equals 2, k equals 4, and so on and so forth. So k equals 2 is going to give us zeta of 4 minus 1. Then we have zeta of 8 minus 1, and so on and so forth. And here we're just going to get zeta of 4, zeta of 8, zeta of 12, and so on and so forth. So now let's look at the extreme left-hand side and the extreme right-hand side. We have this on the left, this on the right, and so that gives us this nice identity, which is given by the sum k equals 1 to infinity of the value of the zeta function at 4k minus 1 equals this 7/8 minus pi over 4 e to the 2 pi plus 1 over e to the 2 pi minus 1. So I'm going to clean up the board and then see what we can get from taking the difference of these. Okay, so on the last board, we saw a nice identity that you can forge by taking the sum of these two identities, which we constructed via generating functions. Now let's see what we can get if we take differences of these. So I'm going to take 1/2 S1 minus S2. And now notice that's going to be equal to 1/2 the sum k equals 1 to infinity of 1 minus negative 1 to the k, zeta 2k minus 1. So let's look at why that's the case. Well, I'm subtracting these two. Again, they have this like term, which is zeta of 2k minus 1. The coefficient of the first one is 1. The coefficient of the second one is negative 1 to the k, so that's what we get. Okay. Great. Now, if we subtract the two right-hand sides, we're going to have 3/4 minus 1. So that's going to be minus quarter. And then we'll have plus pi over 2 e to the 2 pi plus 1 over e to the 2 pi minus 1. And then we have to multiply the whole thing by a half because of this half out front. All right, now we can do the same trick that we did before. So notice that this is equal to 0 if k is even, because if k is even, we have 1 minus 1, and this is equal to 2 if k is odd. So that's going to give us on the left-hand side the sum 1/2 and 2 is going to cancel, so we're going to have the sum k equals 1 to infinity, where k is only an odd number of zeta 2k minus 1. So that's what we get on this left-hand side. And then on the right-hand side, well, we're going to get minus an eighth. So 1/2 times 1/4 is an eighth. And then plus pi over 4 e to the 2 pi plus 1 over e to the 2 pi minus 1. Okay, now we can reindex here. Since all we want is odd values of k, what I can do in this case is replace k with 2k plus 1, like that. And notice that's going to change my bounds of integration to k equals 0 to infinity. And then that's going to make this sum look like the following. We have the sum k equals 0 to infinity of zeta of 4k plus 2 minus 1. Okay, so let's see why that's the case. So why is it 4k plus 2? Well, I've plugged 2k plus 1 into 2k, so that's going to be 2 times the quantity 2k plus 1, which is obviously 4k plus 2. So that's what we get on this left-hand side after doing that. And then on the right-hand side, I can just bring that down. So we have minus an eighth plus pi over 4 e to the 2 pi plus 1 over e to the 2 pi minus 1. So we've got a nice new identity. All right, I'm going to clean up the board and we'll look at a summary. Okay, so let's summarize. In that previous video, we had this sum of k equals 1 to infinity of zeta 2k minus 1 was 3/4. Then earlier in this video, we proved that the alternating sum, k equals 1 to infinity minus 1 to the k, zeta 2k minus 1 was 1 minus pi over 2 e to the 2 pi plus 1 over e to the 2 pi minus 1. Then we put those together in a symmetric way and an anti-symmetric way to get these two sums. So the sum k equals 1 to infinity of zeta 4k minus 1 is 7/8 minus pi over 4 e to the 2 pi plus 1 over e to the 2 pi minus 1. And then here we have zeta of 4k plus 2 minus 1 is minus 1/8 plus pi over 4 times this quantity e to the 2 pi plus 1 over e to the 2 pi minus 1. And now I kind of leave you guys with the following question, which would be quite technical, but would use the same sort of strategy. And let's say, what if we take our original generating function, so that's this sum of zeta 2k minus 1 x to the 2k. Recall that that was x squared over x squared minus 1 plus 1/2 times the quantity 1 minus pi x cotangent pi x, and set x to this 8th root of unity. So in other words, 1 over root 2 plus I over root 2. So this has the property that x to the 8th equals 1, and in fact x to the 4th is equal to negative 1, x squared is equal to I, and x to the 6th is equal to negative I, and so it trends around the unit circle like that. So what would happen in this case? So what kind of identities would pop out of that? All right, this is a good place to end.